Hello everyone, welcome back to Everything Swift. Today we'll be tackling Leetcode question 142 titled Linked List Cycle Part 2. Yesterday I just dropped a video which is linked list cycle that refers to the part 1 of the question, and if you haven't checked out that video, please feel free to do so because we'll use the concept from that question, and we'll definitely have to use that in this question. So please do check that video out and then come back to this video. So essentially this question, the only difference between this one and the previous one, part 1, is basically we need to find where the cycle begins. In part 1, the question is asking us to just prove that this linked list has a cycle within it, right? In this question, we are supposed to find out where does the intersection or where does the cycle begins. So this is a continuation of that, right? So referring to the first video, the strategy that we use to solve the first question, the linked list cycle part 1, is using an algorithm called Floyd's cycle detection algorithm. So please feel free to check out some of the online resources out there. There's a lot of resources out there that does even some animation to prove the math that this algorithm actually works. So just to recap, this Floyd cycle detection algorithm consists of two parts, which is the first part that we use and saw in the first question, linked list cycle part 1, is where proving that the linked list has a cycle, right? And in this question, we are basically doing part 1 and part 2 together. We're supposed to find where the cycle begins. Essentially, finding out where the starting point of the cycle can't spell, cycle or intersection, right? So in this question, we are basically doing part 1 and part 2, right? So essentially, Floyd's cycle detection algorithm is comprised of using this concept called slow and fast pointer. Essentially, what will happen is the fast pointer will traverse through the linked list 2 times faster than the slow pointer. And if it meets the first time inside the potentially while loop here, it proves that the first part that this linked list has a cycle, right? After that, what we have to do is we're going to reset the slow pointer back to the head and then traverse again. And at this time, the fast pointer will only traverse once, and the fast pointer is still inside the cycle. But this time, in the second loop, when they meet each other, they would be meeting at the intersection point, right? So I highly recommend you guys check out this algorithm from the online resource out there that provides explanation, because it really does prove how this algorithm works, right? But this is just a summary of it, that it consists of two parts, right? So whenever we see a linked list cycle kind of question, Floyd's algorithm is probably your go-to solution here, using slow and fast pointer, right? So let's go ahead and try and solve this question here. I'm just going to do the usual check. If head equals to nil, return nil. And as I always mention in my other videos, like in the world of Leetcode, unless specified in this question, we probably don't need to worry about this case, but it's just a habit of mine, because in the real world, we could potentially have a parameter that is nil, and this is just sort of like a fast optimizer for us to exit this function scope as soon as possible. So it's just a tiny bit of performance improvement. So as I mentioned, Floyd's cycle detection algorithm consists of a slow and fast pointer. So I'm going to set that up. Slow equals to head and fast equals to head, right? Here we're going to do a repeat where slow equals to slow dot next and fast equals to fast dot next dot next. And what will happen is the condition is when slow is not equals to fast, right? And then here, what we're going to do after that, so this first part is just to prove that the linked list has a cycle, right? So when they intersect the first time, they are actually intersecting inside the cycle, right? And then after that, we are going to our task is supposed to find out where does the cycle or intersection begin, right? So for that, we have to set back slow to equals to head, right? It goes back to the starting point outside of this intersection, outside of the cycle. But the fast pointer, the fast node, is still inside the intersection. And now this time, both the pointer will traverse only one step instead of two steps. Fast will also traverse one node at a time instead of two. And at this time, when it intersects, it will intersect at the starting point, right? So if while slow is not equals to head, what will happen is slow equals to slow.next and fast equals to fast.next. Sorry, slow is not equals to fast. And then what will happen here is we can return, essentially we can return slow or fast because we are intersecting there, and this slow pointer now or fast pointer will refer to the intersection, the starting point of the intersection, right? So let's go ahead and run this and see whether it works. And there we go. That is the answer. Seems to be working fine. Go ahead and submit this, and hopefully that works. And there we go. Is correct. We passed these test cases. So yeah, so this first loop here is proving the first point, the first part of Floyd's cycle detection algorithm. And the second one is proving the second part, which is to find the starting intersection point, the beginning point of the cycle, right? So yeah, I hope this video helps you to understand or try and solve the linked list cycle part 2. If you haven't already, as I mentioned earlier in the video, please feel free to check out the linked list cycle part 1, which I dropped the video yesterday. So part 1 is basically just ending in this first solution here. Part 2 is basically the combination of both, right? So do check these two videos together, one after another, for better understanding. And yeah, I guess that's it. If you guys find this kind of video helpful, feel free to subscribe to this channel. I'll be posting more videos from here on now. And as always, thanks for your time. Take care and bye bye.